Okay, so welcome to this afternoon's webinar on the challenge of natural hazards, particularly looking at the impact of climate change on Iceland's glaciers. At a time when students across the world have been skipping school to raise awareness about the climate emergency and to sort of protest about ensuring that we have a concrete action for our planet and their future, it's never been more important to ensure that their education has a central and visible part to play in the international response to climate change. After all, bottom line, they will be our leaders in the future. And so awareness and visibility now will ultimately lead to more informed decisions that they will make in the future. It's a fundamental part of the national curriculum, as we know, and I've just been reading recently about some numerous attempts to actually sort of like increase the status within our national curriculum and not just look at it from a science or a geography point of view, but also look at it from a historically point of view as well. Today, we are really fortunate to have with us Richard Waller from Keele University. I've had the absolute pleasure to work with him over the last few years. He's passionate about Iceland, about climate change, and about supporting students' transition into higher education. So therefore, we have quite a lot in common. Richard is a senior lecturer in physical geography at Keele University, and today he's going to look at the challenge of natural hazards, particularly looking at the impact of climate change in Iceland and on the glacial landscapes over there. So I'm going to hand over now to Richard, and I will come back to you at the end.
All right, thank you, Karen. Thank you for the introduction, and a good afternoon to everyone. Thank you for taking time out of your busy days to join us. Obviously, I wish I was with you physically in person, but I'm delighted to have this opportunity to share this webinar with you, which Karen has already introduced. For those of you who don't know me already, my name's Richard. I work as a senior lecturer in physical geography at Keele University. Have a variety of different interests, primarily within glacial and paraglacial environments. Also in terms of supporting student transitions between GCSE, A-level and university geography, and developing a bit of an interest in electrified transport as well, but that's maybe a little bit of an aside, something for another occasion. And I've had a long-standing kind of connection with Iceland, as probably some of you who are involved in this webinar know. I'm thinking of certain individuals. I've got a particular interest at the moment in terms of certainly the glaciology and the glacial geomorphology of Iceland. And that's a research interest which is still ongoing. But that was really developed as a result of visiting Iceland for the first time as an A-level student when I was at school in 1989. This is a picture of me many moons ago when I still had some hair. And indeed, this was my equivalent of my NEA, as it was back in the day, working near Vatnajökull. And it was the first opportunity for me to visit Iceland and to see glaciers for real. And that was a trip that was organized by Arctic Experience, which was the predecessor for Discover the World. And since then, Discover the World have assisted us in terms of running year 2 physical geography field excursions to Iceland ever since 2005, obviously with a bit of an aberration this year. And I know that we'll all be keen to, for those who have been out to Iceland before, be keen to get back there. If you've not, then hopefully this session today will give you an insight into what a fabulous natural laboratory it provides. So what I want to do in this webinar today is to run through a number of, for those of you who are not necessarily all that familiar with Iceland, provide a very brief introduction to what is often referred to as the land of ice and fire, which provides an initial introduction to some of the natural hazards which we might expect to be associated with this very special country. Looking at some of the natural hazards associated with that interaction between the glaciers and the volcanoes in terms of ice-volcano interactions, and then a specific natural hazard which has an Icelandic name to it, or jökulhlaups, as large glacier outburst flood events. Then to kind of focus a bit on the impact of climate change on Iceland's glaciers, which is becoming ever more apparent and dramatic, before finishing off with one of the kind of indications of why this, what the future hazards might be in store related to this rapid deglaciation of Iceland, and to introduce a concept which some of you may be familiar with, some of you might be unfamiliar with, which is the concept of paraglaciation. I'll try and keep an eye on the chat box, but it's quite difficult to kind of do that whilst sharing the screen. So I will try and make sure I leave some time at the end to return to questions. I'll also provide my email address and my sort of Twitter handle as well. So if you've got any questions, do feel free to get in touch with me after the session as well. So starting off with a quick introduction to the land of ice and fire. Then if we're looking at Iceland, then the first thing to bear in mind is that we have a country which is situated astride a major plate boundary, situated astride the divergent plate boundary of the mid-Atlantic ridge. And in addition to that, then we have the association of Iceland with a hotspot or a mantle plume, which indeed was the same mantle plume which has been central to the formation of the North Atlantic in the first case. And this association with both the divergent plate boundary and the mantle plume means that Iceland is a country which is associated, or has been associated since its genesis, with very significant amounts of volcanic activity. So if you look at Iceland, and Iceland is geologically very young, you can see that these areas of blue, which the oldest parts of Iceland material was only erupted about 3 million years ago. So the exposed part of Iceland is geologically very young. And then as you get closer to the areas of active rifting, then these are the areas where we've got the most active processes, both in terms of the seismicity, as we'll see in a moment, in terms of the volcanic activity as well. So the mid-Atlantic ridge comes onshore just off the Reykjanes Peninsula, and then we've got the active rifting here, and then the active rifting which kind of carries on through here and then heads out into the North Atlantic. And you can see, in general terms, then that expansion, that crustal divergence is of the order of 2 centimeters per year, which is in combination with the volcanic activity is associated with the growth of the country. And of course, I won't say much about this, but it is associated as a consequence of that with the tectonic activity. And this was a map I just took a couple of days ago, and you can see this cluster of earthquakes around the Reykjanes Peninsula, quite a lot of seismic activity there at the moment. This cluster, for example, around a volcanic center I'll mention a little bit later on, a place called Bárðarbunga, and you can see this cluster of volcanic activity, seismic activity around the north coast as well. So there's always, and I think last week there was something like 3,000 or 4,000 recorded earthquakes. Obviously, the majority very small, but recorded earthquakes in Iceland during the course of the week. But of course, there's the association not just with the tectonic activity, but also with the volcanic activity as well. So there's a connection between the two. So the areas of active rifting are the areas of active volcanic activity, and we have the western volcanic zone, the eastern volcanic zone, and the northern volcanic zone. And these, what look like kind of strange fried eggs, these are the locations of what are seen as the active volcanic centers. And there's roughly about 30 active volcanic centers located within Iceland, which have shown activity over historic times. So we'll return to a well-known example shortly that I know Karen has talked about quite a bit recently, and has a session, a webinar to showcase that you can access on YouTube as well. But the other thing to bear in mind is looking at Iceland, we're looking at a location which is just subarctic, just south of the Arctic Circle. And as a consequence of that, we are in a situation where we have a cooler climatic regime than we do in the UK. So you can see here mean annual temperatures of around 0 degrees C, below 0 degrees C within the highlands, just above 0 degrees C around the south coast, where we have the impact of the Gulf Stream. And being stuck out in the middle of the North Atlantic, then we have significant amounts of precipitation as well. You can see here in terms of some of the high mountains and the areas of the active ice caps, we've got up to sort of 5,000 millimeters of precipitation per year. So as a consequence of that combination of the cooler temperatures, but in particular very significant amounts of precipitation, much of which falls as snow, then we have the formation of a series of large ice caps, of which Vatnajökull is the largest one, the largest ice cap in Europe. I think they cover about 11% of the land area of Iceland. So we have Jökull, Vatnajökull, and then we're looking down at Mýrdalsjökull and Eyjafjallajökull. So, very, very obvious in terms of any of the satellite imagery that you can see for Iceland. So it's really when we start to then think about those two key features in combination, and we start to think about the volcanic activity, but also when that volcanic activity interacts with that with those glaciers and those ice caps, that we start to generate the distinctive natural hazards for which Iceland is well known. And this is, this opening image is the case study of Eyjafjallajökull, which you'll be all familiar with, or which many people throughout Western Europe and North America became familiar with in 2010. There is a broader relevance of that, for any of you who travel to Iceland and you're interested in terms of the development of the Icelandic landscapes more generally. A number of these central volcanoes, some of which are inactive now, are associated with the so-called table mountains or tuyas. So we've got these flat-topped and steep-sided mountains. And these reflect the active eruptions that took place at a time when Iceland was glaciated. So during the glacial maxima. So in these situations, you would have had the eruption taking place underneath the ice cap, generating initially things like pillow lavas and then material which is known as hyaloclastite, which is when the explosive activity fractures that material to produce this fine-grained material. And then eventually, when if the eruption continues and it breaches the top of the ice cap, then you end up with conventional lavas being produced on the top, which provide the flat top of these tuyas, or what the Icelanders refer to as stapi. And Herðubreið in northern Iceland is one of the best known examples of that. And there's lots of locations where you can go to in Iceland to see fantastic exposures of this. In this case, you can see these pillow lavas here, and then you can see these nice bedded hyaloclastites, these tuffs related to the explosive activity, which are both sort of signature features of this subglacial volcanic activity and these interactions between the active volcanoes and the glaciers. And they're really important in the generation of the Icelandic landscape. Anyway, if we return to this image, then number 13, unlucky for some, was a volcano which came very much to the public attention and caused all kinds of problems for newsreaders around the world in 2010 when it erupted. And of course, we're looking at the eruption of Eyjafjallajökull. And an interesting eruption, and it had two distinct phases. You had an initial phase where the eruption occurred in a place called Fimmvörðuháls, which was an area where the eruption is a subaerial eruption. So the eruption was occurring into the air, and we had these classic sort of fire fountains. It was kind of referred to as a touristic eruption. So there's the opportunity to see the fire fountains generating these scoria cones, lava flows, a waterfall, and also these lava falls as well. And you can see this is where that initial phase of the volcanic activity occurred. And then you can see the lava flows snaking their way northwards from that eruption site towards the valley of Thorsmork. And the issue then was the eruption site, which is started over here, the locus of the eruption then shifted to the west, and a second phase of the eruption, which caused all the problems, occurred underneath the ice-filled caldera of Eyjafjallajökull itself. And this is when we had the second phase of the explosive subglacial eruption that was focused underneath this summit crater, lasting from the middle of April to late June in 2010. The initial signs of this, again, were the seismic activity, a big cluster of seismic activity in early May that showed the ascent of magma towards this different eruption site. And then, some images of this eruption, which I'm sure is well known to many of you. This is you see the caldera walls around the edge of Eyjafjallajökull, and the eruption taking place in the central part of that. and these huge columns of ash which are being generated. And the explosive activity, of course, was associated with that interaction between the erupting basaltic magma and the ice within that caldera. So the ice was rapidly flashing to steam. You had that massive, that very significant volumetric expansion where that steam's been generated, which fragmented the material to produce this ash. So this is known as a hydromagmatic eruption. It's that interaction of the magma with the water that generates this explosive activity. And I think if my memory serves me correct, I think at the peak of the eruption, there was the estimated production of about 25,000 tons of ash were being generated every second at the peak phase of this eruption. So what we had in essence was people liken this to something of an atmospheric pollution event. We had a source, which was the erupting volcano. We then had the pathway in terms of the atmosphere, and we had a big high pressure system or big anticyclone within the North Atlantic at the time, which was then merrily feeding this ash down towards the UK and UK airspace. And then the big concern at the time was the receptors in terms of aircraft engines. And so, of course, we had the lockdown of airspace for a good week or so, and the very significant economic impacts as a consequence. And something which I don't think has really been trailed much in the media, which I think is a little bit of a shame, is that we were really caught short in the UK at the time. We didn't really have much, if anything, in the way of an ability to empirically observe or monitor the ash coming over the UK. So one of the big developments after the Eyjafjallajökull eruption has been the development of a volcanic ash observing network, which is based around a series of fixed and one mobile surface-based LIDAR. LIDAR is a laser-based system which can then be used to detect this ash with the hope therefore we'll be better prepared in the future to be able to identify and monitor the location, the height and the density of any ash cloud which is sent within our direction. So we should hopefully be rather more resilient than we were in 2010. So that moves on to another natural hazard, which is well known in Iceland and is another product of the interaction between volcanic eruptions and the ice caps that occur within Iceland. And these are what are known as jökulhlaups. So jökulhlaup, which literally means glacier run. Jökulhlaups refer to the massive flood events that accompany the huge amounts of meltwater that can be generated when a volcano erupts underneath an ice cap. And the most famous recent example of this was an eruption in 1996, which came out of the margin of this large glacier called Vatnajökull. And you can see it occurred in November. So the Sander surface here is covered in snow, and you can see all of these dark areas are areas where you've got floodwater, which is issuing out of the glacier margin. And this glacier margin is about 23 kilometers wide, so you can get a little bit of a sense of the scale there. In terms of the interaction here, Vatnajökull in particular, I think is quite interesting in that we can see we've got the western volcanic zone, which comes under and intersects with the western part of Vatnajökull. I mentioned Bárðarbunga earlier on. So Bárðarbunga and in particular Grímsvötn are two of the most active volcanic systems, historically active volcanic systems in Iceland. Grímsvötn, in fact, is the most active volcano in Iceland. It's situated underneath the western portion of Vatnajökull. But the eruption which took place in 1996 took place in a place called Gigjukvísl, which was basically a fissure system which erupted, which was located in between these two major volcanic centers. And what happened was the eruption took place here, but the water then drained and accumulated within the Grímsvötn caldera before it reached a point at which it then rapidly discharged out through Skeiðarárjökull and out onto Skeiðarársandur, which is the largest active outwash plain in the world. And this highlights the impact of these very large volcanically induced jökulhlaups, which are some of the biggest flood events that we see anywhere on Earth. So the eruption at Yelp is estimated to have generated about 3 cubic kilometers of water, which then accumulated in Grimsvötn before it was then released as a jökulhlaup, which reached a peak discharge estimated between 50,000 and 60,000 cubic meters per second. To put that into context, I think, you know, a reasonable flood event on the River Thames, you're talking about things like 200 cubic meters per second. So, you know, you're talking of things which are, you know, orders of magnitude greater than the classic types of flood events that you would see in UK river systems. There is not much in the way of infrastructure on Skeiðará Sanda for obvious reasons. But what infrastructure there was on Skeiðará Sanda was severely damaged, and still you had the destruction of bridges and power lines, and $16 million worth of damage that were caused by this flood event. And it's interesting to note that this is a big flood event, but it's still relatively small in comparison to the flood event which occurred in Katla. I said 1914, I think it's 1918. Which is estimated to have had a peak discharge of potentially up to around 250,000 cubic meters per second. And Katla, as Eyjafjallajökull's next door neighbor, is one of the volcanoes in which Iceland, you know, the Icelanders and the Icelandic authorities are always looking at, and it hasn't erupted for that time period. And they're not necessarily like buses, but they, you know, there is a concern that an eruption of Katla, the key impact of which will be a massive flood event, is overdue. So some images about what this eruption looked like in 1996 at Vatnajökull. The initial sign was the production of these so-called subsidence cauldrons. So what was happening here was the eruption was taking place subglacially. The meltwater was evacuating the site, and the surface ice was then collapsing as a result of that. So this was the first sign that an eruption was ongoing. Within 24 hours, the eruption burnt through about 400-500 meters of ice, and you can see the eruption column appearing here. You can see it's white. That shows that we're generating steam, primarily in this situation related to the melting of this ice. You can see there's an aircraft for scale. And then the meltwater flowed from the eruption site. You can see the hot water was such that it was actually burning that channel, and it was flowing southwards towards the caldera of Grimsvötn, where it was then temporarily impounded. And then after a period of time, there's some great stories about that people were waiting for the eruption. The world's media went and were waiting for this jökulhlaup to take place, and they waited and they waited, and it didn't happen. And then eventually they got bored, and they jetted off to cover some other stories. And I heard that for the majority of the cases, it was just after they'd all flowed elsewhere that the jökulhlaup took place. But this shows a picture the morning after the second morning of the jökulhlaup, and again you can see all of the meltwater, the debris-rich meltwater, which is discharging the ice margin. And this is one of the major sort of conduits that's related to where the water burst out of the glacier margin. Plain for scale. Here's the glacier margin. These are literally house-sized blocks of ice that are being quarried from the ice margin and are then being saltated along within the flow. And it was the production of those icebergs that we'll see in a moment, which was the key cause of the damage. Here's a good old flood hydrograph of this particular flood event. These relate to the individual conduits or outlets that are active at different moments in time. But if we look at the cumulative one, we can see this is kind of like suggesting that we reached a peak discharge of just shy of 55,000 cubic meters per second. You can see that we've got a rising limb, which is rising to peak discharge in less than 24 hours, about 16 hours or so. And then you can see again the rapid falling limb back to a baseline discharge. And you had the water that initially was kind of burst out from the glacier margin on the western side. Then we had the majority, the big focus in terms of the efflux of the water during this flood event was in the central part of the glacier, what was known as the Gigjukvísl double embayment, and then the final phases of the flood event came out from the western side of the glacier margin. But as I say, the margin of Skeiðarárjökull is about 23 kilometers in width. You know, so it gives you a sense of the area that was affected. I think one of the interesting things about this was the huge pressures that were associated with this water basically forcing its way down to the glacier margin. Was that in the initial stages of the flood, the initial flood waters burst out onto the glacier surface. So they were basically rising up through about 150 meters worth of ice to burst onto the glacier surface, a full 2 kilometers or so up glacier of the actual margin itself. And I was involved in some research in this, and we went to the year after to look to see whether we could find any evidence of these original supraglacial outlets. And what we found, we did find that. We found that these are basically the floodwater sediments, these dark material. This is like the tephra, the ash type material. But within that are chunks of glacier ice and chunks of glacier bed that have been ripped up from the bed and are then being forced up these fractures. And now we're located on the glacier surface within these flood sediments, 150 meters above the bed. So that's sort of testament to the violence and the pressures associated with this remarkable flood event. This is what the site looked like the year afterwards. So this is where the double embayment was. You can see why it's called the double embayment. This is where the focus of the main floodwaters were. And you can see that this is where the icebergs were generated, which then subsequently melted out and then have produced these classic icebergs, which are characteristic of these so-called pitted sander or pitted outwash surfaces. And it was the production of these icebergs that did the majority of the damage. So you can see that one of the main bridges across one of the river systems, the River Giu, was basically smashed to pieces by the icebergs that were basically washed down within this flow. So it's the inclusion of those big house-sized blocks of ice that were quarried from that ice margin that were a key component of this jökulhlaup. If you end up looking at Google Earth at this site today, then you'll see here's the glacier margin here. The glacier margin at the time was up here, so it's retreated a full couple of kilometers or so since then. This is where the double embayment was. This is where you can then see all of the kettle holes related to those ice blocks. And now we can actually see the Esker system, this sort of this subglacial conduit. This was what was then feeding the meltwater that was coming out through this double embayment. So I'd always recommend, if you get a chance, go and have a look at the Google Earth imagery around this area. Have a look at the different time stages of imagery, and you could end up getting a feel for the impact that this event had on the landscape around that particular glacier margin. And I was out there with a group of students last year, and I hope you all get the opportunity to get out to Iceland yourself before too long. Provides a really neat opportunity to end up doing some little bits of field work with students, the opportunity to take simple measurements of the size of these kettle holes, estimating their width, their depth, using some sort of empirical equations to identify the size of the ice blocks within that. And then you can provide some first order approximations of the volume and the mass of the ice blocks that were occurring within those systems. Quite a challenge to measure these, particularly when it gets windy, but it's good fun. Moving on to the impact of climate change on Iceland's glaciers, something which is really I've given a lot of thought to and has really become an issue of rather more significant kind of concern for me over the course of the last year or so. And it's been interesting to sort of like reflect on that. I mean, I've been going out in Iceland, as I say, between 1989 and then I've been every year since 1996. And you become just accustomed to the fact that every year you go and visit, in my case, many of the same glaciers, and they will have almost pretty much inevitably have retreated. And we just become accustomed to the fact that the glacier is retreating because that's what glaciers do. But if there's I listened to this podcast between Christmas and New Year, which I'd recommend, which is still available on BBC, part of their assignment, called Iceland, the Great Thaw. So I'd recommend you kind of seek that out, listen to that, well worth listening to that. And it provides some interesting coverage of this very issue, the rapidity of this, and in particular, how both the scientists in Iceland, but also how the lives of local people in Iceland are being affected by this, and really what they make of this in terms of natural versus anthropogenic climate change. So I'd thoroughly recommend that. In terms of a context, of course, we're all familiar with the nature and the rapidity of climate change, but also that sense that the rate of climate change is roughly a rule of thumb is that the rate of climate change within the Arctic, and we can see we're certainly within this bracket, 60 to 90 degrees north. Iceland fits within that area. The rate of warming within that particular area is roughly double that of the global average. So the Arctic, in which we include Iceland in this case, is warming up more rapidly than anywhere else on Earth. And unsurprisingly, this is having a significant issue, or significant impact on Iceland's glaciers. Again, I'm not going to try it here, seeing as it's being streamed on YouTube, and I don't think the two interact very well. But if you get a chance, if you go to the Extreme Ice Survey, then you can find some fabulous time-lapse imagery that provides you with an opportunity to basically to visualize not just the glacier flow, but also the ways in which this is impacting on the recession and the down wasting of glaciers over time, in which we can think about Jökulhlaup as a particular example. And a website I'd recommend here is the World Glacier Monitoring Service Fluctuation of Glaciers browser. Provides you with an opportunity to access data that shows how glaciers throughout Iceland have been responding to that climate change over time. So an ideal resource to get students engaged with. In doing so, they're engaging with an online ArcGIS package as well. So there's typically a requirement in the spec for them to engage with GIS, and that's one way in which they can do that. And so I'll just provide 3 examples of glaciers that I've been familiar with during my time that I've been to Iceland, starting off with Jökulhlaup, which is on the southern part of Mýrdalsjökull, Skeiðarárjökull, and then finally Breiðamerkurjökull, which is located here. If we look at those in terms, so Jökulhlaup, you can see if we look from that sort of Second World War period, retreated by a kilometre, then experienced a bit of a re-advance as a consequence of a period of time when there was very significant amounts of precipitation taking place. But then you can see since the sort of early mid-1990s, we've had that recession of the order of about a kilometre or a bit more than a kilometre over that time period. And you can see the rapidity of that recession taking place. So again, an ideal opportunity to use Google Earth. This is the margin of Jökulhlaup in winter in 2008. If we then end up looking, I think this is about 2018 or so, you can see that this lake has appeared, and we have had the recession of the glacier margin by about 750 meters over that decadal time period. But for anyone of you who have been to that site, you'll be familiar with where the main car park is, and where there's that little hut where people can end up getting their crampons on going for glacier walks. The first time I visited the site in 1996, and I'll just show you a picture taken from about here, looking in this direction. So this is 1996. That was where the margin of Jökulhlaup was the first time I visited. That car park would have been basically underneath the ice margin in 1996. So from that perspective, you can see how far it's retreated over that time period, over that sort of intervening quarter of a century. Another glacier I've worked on, again, Skeiðarársandur, and again, you can see this big outwash plain related to these periodic jökulhlaups. That's how you produce that big outwash plain. Again, this kind of shows that we've had a bit of recession, then it's sort of been stable for a while. There was actually a little bit of a surge event, which are advanced, but again, rapid recession, again, on the eastern side of about a kilometre or so. If I share some photos, again, the first time I went to this site is one of my PhD field sites in 1996. Here's an aerial photograph. It's actually a slide scan. I didn't have a digital camera then. Then the glacier was still at its maximum limit there after a surge event. So this is where the margin was located. Picture in 2012. You can still see the surge limit. You might be able to pick out this moraine limit through here. That's where it was in 1998 when I first visited the site. So in fact, if the active part of the glacier margin is here, we've had recession there of about 2 kilometers, again, during that time period of about a quarter of a century. And of course, I guess one of the most picturesque sites in Iceland, Vatnajökull and Jökulhlaup, that's that's a site where we've got the recession of another large glacier, Vatnajökull, which is retreating in this case into the so-called glacial lagoon. And so we've got even more significant recession there. We've got recession in this part of the margin, which is of up to about 4 kilometers or so in that time period since the Second World War. And Dave Evans and colleagues at Durham have done mapping work related to historic aerial photos of that site. If you were to go there in 1945, just after the Second World War, then the ice margin was pretty much close to where that visitor center is located, and you only just had the appearance of Jökulhlaup. If we then go to 1965, you can see where it's located there. And then if you go to the modern day, you can see I wasn't able to kind of quite transpose these, but you can see where it's located now. This is 3.78 kilometers. The actively calving ice margin is retreated by about 5 miles or so away from where it was in 1945. And that shows the rates of ice recession are generally much greater if we're in a situation where we can have the loss of ice through the process of calving, which is related to the production of this lake, and which will ultimately see the margin of Vatnajökull retreating into a lagoon. Oh, wait, sorry, into a fjord. Not just that, then I think this has started to raise kind of concerns about that awareness of not just that glaciers are retreating, but glaciers are disappearing. There was the commemoration and memorialization of this within Iceland as part of a project in which Andri Snær Magnusson, who is a bit of an inspiration for me, an Icelandic author who a number of you might know. There was the commemoration of the loss of a glacier on a shield volcano called Ök, the disappearance of Vatnajökull. And I'll just read the caption here. Ök is the first Icelandic glacier to lose its status as a glacier. In the next 200 years, all our glaciers are expected to follow the same path. This monument is to acknowledge what we know, what is happening, and what needs to be done. Only you know if we did it. August 2019, 415 parts per million CO2. He's got a book coming out imminently, which is focusing very much on this issue on time and water, which is really kind of like looking at the impacts of climate change on the recession of glaciers. And I think the thing that I've taken home from that, and the things which he's really given me pause for thought about, is this, the time periods over which this is taking place. And it's caused me to reflect that in about half of my time, half of my life so far, I've seen the glaciers of Iceland in many cases retreat by several kilometers. And then there is the prospect that by the time that he puts it, his grandchildren by the end of their lifespan could witness the complete disappearance of glaciers within Iceland. So really looking at the rapidity of that change in the context of human lifespans. And just to kind of put that, here was some modeling work that was published in 2018. If we look at the major ice caps of LANDSLIDES, Hofsjökull and Vatnajökull, and we look at their modeled extent going forward in time, then you can see in a worst case scenario that by the end of the 22nd century, 2190, the model predicted that LANDSLIDES will have completely disappeared. Hofsjökull will have almost completely disappeared, as will be the same case within the southern part of Vatnajökull. So there is that very real prospect, if things continue in the same trajectory as they are at the moment, that within those kinds of timescales, the majority of Iceland's ice caps will have completely disappeared. Another thing which surprised me and which I wanted to share in this webinar was that the ice caps and glaciers are rather more sensitive to and vulnerable to climate change than we might otherwise think. It's now appearing that the glacier or the ice cap on LANDSLIDES, for example, completely disappeared during what's known as the Holocene thermal maximum. That it then reformed after about 3,000 years or so ago to produce, to reach its near sort of current maximum extent. And now we're seeing the even more rapid disappearance. So we see glaciers and ice sheets as being something almost permanent in the landscape, but in reality, they are very, very sensitive to climatic changes as a result of those connections with temperature and precipitation. And this is a rather busy diagram, but what this tries to do is to illustrate, again, based on modeling work, it shows the lifespan of the ice caps in Iceland. The blue figures show, this is going back 7,000 years before present to the modern day, and they're looking into the future. And the blue scales are trying to kind of, well, when did that glacier form? Some of the glaciers persisted right throughout the Holocene. Others have formed more recently. The grey lines show when they've been alive, if you like, to use that metaphor, and the red line shows when they're thought to die. And you can see that the predictions again of this modelling work have suggested if we end up with rapid warming taking place, that these many, if not the vast majority of Iceland's ice caps could then disappear. So the thing I wanted to just finish on was then to look at, well, what would be the implication, or what are the implications of this rapid deglaciation of Iceland for the kinds of natural hazards that are likely to face the population of Iceland and any visitors traveling to Iceland. And in that kind of context, I wanted to, it's the potential for very significant landslides and for what's known as paraglacial activity, which is something that we should focus on. I know that the concept of paraglaciation or paraglacial activity is probably something which might be unfamiliar. It's a concept in geomorphology. It refers to a series of what are known as non-glacial processes which have been affected by glaciation. So the general idea is that as a landscape deglaciated, as a glacier, as an ice sheet retreats, then we actually get a peak of geomorphic activity as the landscape adjusts to the removal of that ice. And then, so the amount of geomorphic activity that's taking place increases during that phase of deglaciation, and then it diminishes down towards a longer term baseline. And it's this longer term period of time in which we get this elevated geomorphic activity, which is referred to then as this paraglacial period of landscape adjustment. And one of the best known processes of landscape adjustment to deglaciation relates to a process which is known as debuttressing, and therefore relates to the potential for very, very significant mass movement taking place. So as you well know, the active glacial erosion has a tendency to generate glacial troughs, which are steep-sided. But whilst the glacier is still within that valley, then the presence of the ice prevents failure taking place. The presence of the glacier buttresses the slopes. However, when the glacier then retreats, we're left with a steep slope, which is then unsupported. And in particular, if we've got sort of incipient fractures or potential lines of failure within those mountainside, then there is the potential for very, very large landslides or rock slope failures to take place once the glacier down wastes or disappears. So this is a well-known process of landscape adjustment, which is a key natural hazard that we need to look out for. And there is plenty of evidence of this now being ongoing and starting to potentially accelerate in Iceland. I'll just look at two examples. One, you can actually see the debris here. This is known as Jökulhlaup. So this is looking in the area of around Skaftafell National Park, the campsite's down here. And then also this is a glacier called Svínafells-jökull. This is Skaftafellsjökull in here. So we'll start off by looking at Jökulhlaup. Again, not particularly high quality imagery here, but this is imagery I think that was taken from about 2000, and we can see Jökulhlaup here. If we end up then looking at, I think this is taken from 2012, and suddenly you compare that there's this big area of debris. This relates to a big rock slope failure, which has cascaded down and covered a significant part of that glacier surface. And then if you look at the more recent imagery, it's moved down glacier somewhat, but you can see this big area related to the material that's associated with this rock slope failure. And just to kind of highlight again, really great opportunities to end up using the GIS functionality within Google Earth. So if students download Google Earth Pro, which is freely available, then you have got that functionality to actually map features out. So you can map out the perimeter, map out the area, and then if you made some approximations in terms of estimated thickness of that, you could very easily try and identify, well, what was the volume of material which had been affected by that activity. Bit difficult to make out. Here's a plane photo I took a few years ago, but this is looking up the valley of Jökulhlaup, but you can still see this dark area here is where you've still got this material. It's actually protected the underlying glacier ice. So this doesn't show the thickness of that. It actually shows how it's actually protected the underlying ice from melting out after that took place. But the big concern at the moment for a couple of years now has been on Svinefellsjökull, which is a very popular glacier for tourists to visit. And just tucked around this corner, farmers in 2014 noticed a large crack opening up, which the Icelandic authorities have been monitoring. And there has been a fear for some time. Certainly, there was a lot of concern and people being advised not to visit the site. A fear that there was a potential for an area of about 1 kilometre square to fail, resulting in the movement or the displacement potentially of 60 million cubic meters of material, and the potential threat of a potential sort of displacement wave or a little mini tsunami that could relate if that material then came down to the lake at the glacier margin. But as far as I'm aware, that event has not yet occurred, but it's still very much a kind of concern in this particular vicinity, and certainly something that we should look out for as we consider the range of different natural hazards that will face this area in the future. Okay, so just to summarize then, it's the combination of the volcanic activity in Iceland and the presence of these glaciers and ice caps that leads to the development of a whole variety of different and very distinctive natural hazards, which have affected Iceland, continue to affect Iceland, will affect Iceland in the future. And it was probably the eruption of Vatnajökull in 2010 that certainly brought the disruptive impacts of so-called hydromagmatic eruptions to the public attention when they suddenly found that their flights had been cancelled and they couldn't travel. I think the estimated economic losses of that were about 5 billion euros within Europe alone. And those kinds of events are almost certain to occur in the future. Hence the efforts to try and make us more resilient to the potential impacts in the future. And then, of course, if we end up thinking about the impacts of this volcanic activity on the glaciers and the rapid production of significant amounts of meltwater, which can then be released catastrophically, then it's these volcanogenic jökulhlaups that relate to these, some if not all of these volcanic eruptions that can produce some of the most dramatic and spectacular flood events that we see anywhere on Earth. The impact of rapid Arctic climate change, or within the subarctic in this context in Iceland, is becoming increasingly apparent. And the thing which I would reflect on here, and hopefully there's a number of people in the audience who, like me, have been out there for a number of years, it is the way in which you can appreciate that significant recession that's taking place over, well, actually fractions of human timescales, which has been the thing which I've been reflecting on most last year. And in the intervening time period, as a result of thinking and reflecting on the work done by Andrew. And it really sort of highlights that these, rather than being very sort of permanent and resilient features, that Iceland's ice caps are actually far more sensitive and far more vulnerable to climate change than we might have previously imagined. And their disappearance and their neoglaciation of ice caps during the Holocene serves to illustrate that point. And as we look forward and we end up thinking about the ongoing recession of these glaciers within Iceland, then it's the landscape adjustment and these so-called paraglacial hazards that will accompany that deglaciation which are the things that I think we really should look out for, and the potential for large landslides. These kind of same issues affect areas like the European Alps, for example, major concerns there. But again, the large landslides and the example of Síðufossjökull provides a graphic illustration of that, are likely to be the suite of hazards which will cause mounting concern in the years to come. Anyway, thank you very much for your attention. I'll just leave you with some cited references, just so you can see those within the recording. I will provide a copy of the PDF back to Discover the World for anyone who wants a copy of those. And just to leave you with my kind of contact details. If anyone's got any follow-up questions, then do feel free to email me through that address there. Or I have got a kind of like a Twitter handle as well, in which you can get in touch. So thank you very much. I hope that's been useful, and I shall try and figure out how to stop the slide share. Thank you.
Thank you, Richard. Honestly, it was really just the most wonderfully visual and informative presentation. Absolutely fantastic. And it really shows what Iceland is sort of like open to at the moment, one with the volcanoes, but also, you know, the impact of climate change as well. And I think climate change is something that's been on the news a lot recently, particularly in the Arctic regions. We were looking at the Siberian plains just yesterday on the BBC, and I've been watching quite a lot of documentaries on Sky about the relationship between the Arctic Circle areas and you know, what's happening there. I think what I found really interesting today was about the paraglacial impacts, and we know sort of like, you know, that we've had to stop people going to Subsidence recently just because of this worry of the landslides and the rock falls and everything that's happening there. So, you know, it really is really very, very evident. So thank you, really, really good. This does end our webinar series for our lockdown period. Actually, we do have another one in the middle of August, which is about travel in a COVID world. So if you do want to sign up to that one, it's actually the day after results day for A-levels. So it's on August the 14th, I believe, or 15th. So please do sign up for that. As Richard said, we can provide you with a copy of the PDF for this particular webinar. And you may be interested to see our other webinars, which are all either on our YouTube channel or downloadable from our website. And if you've got any questions, or if you want to take another look at our resources, please do just let us know. Thank you very much, and stay safe, everyone, and see you soon. Bye.